plastic bag, drifting through the wind, wanting to start again.
Hi guys, today we are going to start a new unit, and the unit we are going to start has to deal with circular motion, and most specifically we are going to be dealing with what's called uniform circular motion. So what that means is that you are moving at a constant rate in a circle. So this is chapter 6 if you are following along in your textbook. And everything that moves in a circle, the first word we're going to define for our unit is called centripetal acceleration. So everything that moves in a circular path experiences what's called a centripetal acceleration. And what this is just acceleration directed towards the center of a circle. So if we were to look at a circle, let me go back one slide. So if we were to look at a circle, as an object travels in a circle, what centripetal means here for us, that's a really cruddy circle, but the acceleration is directed always towards the center of the circle, or towards the center of the circular path. So if I'm traveling around in a circle this way, my acceleration is actually directed towards the center. Why this is, we're going to talk about a little bit more in the upcoming sections, but for right now, you just need to understand that this is how it is. So we learned before that acceleration is change in velocity over time. So in all of our instances before, something was speeding up or slowing down. It was changing its velocity, so we knew that it was accelerating. But when something travels in a circle, even if that something is moving at a constant speed, it still has a centripetal acceleration, even though the change in speed is 0. So how does that happen? Well, remember that velocity is direction and magnitude, right? Velocity has a magnitude and direction. We've only been concerned with situations where the magnitude changed, right? The initial velocity was 10 and then it was 20, or the initial velocity was 10 and then it went to 0. Those are both examples of when it's accelerating. We haven't really talked very much about what happens when an object changes its direction. And in that instance, its velocity is changing even though its magnitude may be staying the same. So if the velocity changes, it has an acceleration. So when something moves in a circle, we sometimes talk about its tangent velocity. Another way to talk about this, and I'll talk to you about why it's called tangent velocity, but is to call it its linear velocity. But as you are moving, if you look at this graphic, if you look at the black line kind of represents the direction the object is going. So if we take this instant right here, its tangent velocity, or its velocity tangent to the circle, if you guys are not familiar with that word from math, tangent just means against or up next to. So its velocity, its tangent velocity, is going over here to the left. But if I continue making my circle and I look at it at another point down here, well, now my velocity is pointing downward. And all along the way here, my tangent velocity will slowly start to change direction as I move around the circle. That is why I go in a circle, right? It's because I'm moving, but I'm constantly changing my direction at the same time. So this little tidbit right here, again, centripetal acceleration is always pointed towards the center of the circle. So what this means essentially is that you can have a constant speed, be moving in a circle, and have acceleration. And that acceleration is called centripetal. So you guys may have heard these two words, centripetal and centrifugal, or centrifugal, depending on how you pronounce it. But they are not the same. You guys maybe have heard of something called a centrifugal force or a centrifugal force. But those two words mean two different things. Centripetal means center-seeking, right? Centra meaning center, and the pedal part meaning looking for or seeking. Those two words put together, they mean that. So that acceleration is always pointed towards the center. Centrifugal means center-fleeing. So this would be an example of an acceleration that would make something leave the circle or push out from the circle. And in our instances, centrifugal doesn't really happen. It does exist, but we'll get more into the conditions and what it means to have a centrifugal force and all of that in a couple of sections. But for right now, just understand the difference between the vocab. All right, so how do I calculate centripetal acceleration? And well, lucky for us, it's a pretty easy calculation. And all we have to do is take the speed that the object is traveling in the circle, square it, and then divide it by the radius of the circle. So for centripetal acceleration on your formula chart and in everything that we do, it is an A with a little subscript C, so that we are very clear about what kind of acceleration the object is experiencing. This tells us it's going in a circle. So let's look at an example. This one's pretty straightforward. But here, a test car moves at a constant speed around a circular track. If the car is 48.2 meters from the track center and has a centripetal acceleration of 8.05, what is its tangential speed? So, this word you may see occasionally. It really just means linear. It's essentially how fast the object would be going if it wasn't going in a circle. If it was just traveling in a straight line, what would its velocity be? And that's always going to be its tangent speed. So we have I lost my little division fraction line. 8.05 is our centripetal acceleration, and that is equal to the linear velocity squared divided by the radius, which in this case is 48.2 meters because that's how far he is from the track center. So then I'm just going to cross multiply 48.2 to both sides, and I get 388.01 is equal to my velocity squared. And, I didn't finish the problem. And then you will square root your 388, and you should get the tangent velocity, or the linear velocity, to be 19.7 meters per second. All right, so a couple more words we need to define before we can really start talking about circular motion. First is period, and then the second word is called frequency. And you guys might have heard of these in different contexts. But for the period is the time for one complete revolution, or the time it takes for the object to make one complete circle. Period is always measured in seconds, and when we have a period in our equations, it's always a capital T. Right, lowercase t is always just normal time, but period is something special because it tells us exactly how long it takes the object to travel a circle of a certain size. So we denote it with a capital T. One complete revolution. And then the other word we need to talk about is frequency. Frequency is how often something happens. If something is very frequent, it's happening a lot of times per second. So frequency is how many revolutions, or how many times around the object will go in 1 second. And that is always measured in a unit called hertz. The symbol for hertz is Hc, and then the symbol for frequency is a lowercase f. So these two values are inverses of one another. Let's take a look at what that looks like. So frequency is equal to 1 over the period, and period is equal to 1 over the frequency. So, for example, let's look at this real quick without the formula. Well, yeah, we'll just leave it right here. So, if it takes me 3 seconds to make one circle, then my period is 3 seconds, right? That's how long it takes me to go around one time. But my frequency, how many times around am I going per second? Well, if it takes me 3 seconds to get around once, then after 1 second, I've only gone a third of the way around. So my frequency is 1/3 hertz. So another way to talk about period is to put this in terms of velocity. So velocity is 2 pi r over t. If you think about it, this is the exact same thing as distance over time, except this is the circular version. So 2 pi r is equal to a circle's circumference, right? And period is the time it takes to go around that circumference one time. Time for one circumference. So when you divide those two things, the distance, which is the circumference that you are traveling, divided by the period, which is the time it takes you to do that circumference, it's the same thing as just saying regular distance over time. And that will give you the object's velocity as it travels in a circle. All right, so here is another example, and I'm going to go to my whiteboard to do this one because I'm running out of space here. Or there's not much room. All right, so we had an audio CD with a diameter of 120 millimeters. So this is millimeters. Let's just go ahead and convert that because we should know by now that we're probably going to have to. That's 0.12 meters. So then it says it spins at a rate of 540 RPMs. So this might not be something you guys maybe are familiar with, but an RPM stands for a revolution per minute. How many revolutions the object is making per minute. So let's rewrite that under here. 540 revolutions per minute. All right, fabulous. So now it's asking us how much time is required for one revolution. So first of all, this is a velocity, but it's not a velocity in terms that we can use right now. We have a diameter in meters, and then we have this velocity in revolutions. So that's really not going to work for us, right? So let's convert a revolution per minute to a meter per second. That's the unit that we want to get into. All right. So we're going to have to do that anyways for later on in the problem. So one revolution is one circumference, right? So that is 2 pi r. So 2 pi r meters is one revolution. So one revolution has 2 pi. Now our diameter is 0.12, which would make our radius be 0.06. And that's going to be in meters. So our revolutions will cancel out. So now we need to cancel out our minutes. So 1 minute, 60 seconds. And 1 minute. Minutes cancel out, revolutions cancel out. We should end up with a velocity of 3.4 meters per second. All right, we've kind of answered the second question first. I kind of did this out of order, but that's okay. We're going to use this information to go back up and answer the first question, which is how much time is required for one revolution? So we learned that velocity is 2 pi r over t. So our velocity is 3.4. One revolution is 2 pi times 0.06. And all of that is going to be over the period. So when we do that, we should get a period of 0.11 seconds. Double check my math real fast. So divided by 3.4, yes, 0.11 seconds. Fabulous. Okay, so now the next question is how fast is it moving? Well, we already figured that out. And then the last question is asking us, what is the acceleration? So acceleration meaning centripetal acceleration. So our velocity, v squared over r. Our velocity is 3.4. Our radius is 0.06. And then we can divide those two, and we get a really large number, but that is okay, 192 meters per second squared. Centripetal acceleration is typically really, really large because it's telling you how often the object is changing direction per second. And if you're thinking about a CD that's spinning in a CD player and spinning at a 540 times per minute, well, it's making a lot of directional changes very, very quickly. So this number, since it's so large, kind of makes sense. So, all right, I want you guys to try this problem on your own. We will check the answers when you come back to class tomorrow.